Okay, so let's go over exam number 2. So problem number 1 was a circuit that had a 20-volt source, a 2-ohm resistor, a capacitor whose value was not known, but we did know that the voltage drop across the capacitor in its initial condition was 8 volts. We had an inductor that we did not know what the inductor is, but I said the current through the inductor was 3 amps. So the first thing it said is determine all V's and I's in the circuit, right? So you should have V for the supply, I for the supply, V of the 2 ohm, I of the 2 ohm, V of the capacitor, I of the capacitor, V of the inductor, and I of the inductor, right? Those are the ones that you should do. And I'm not going to give you the full answer, but what type of circuit is this? Is this a series or a parallel circuit? Series circuit, right? So if it's a series circuit, what do we know about the current? Lives everywhere. So you know that you've got 3 amps of current that lives everywhere. So based on knowing that you have 3 amps of current everywhere, do you think you could solve for voltage drop? At least one, right? You know what Ohm's law is. And you don't know directly what the voltage drop across an inductor is, but you could use KVL to solve for VL, right? And that was it for problem 1. Questions on problem 1? Fair, not fair? Thumbs up? Any other comments or questions? All right, let's jump to number 2. A 24-volt source, a 3-ohm resistor. We had C1, an inductor. We didn't know the value. And some of these values were left as C's and L's just to make it hopefully easier. If I don't give you a value for C and L, then essentially you can't really look at things from a time perspective. But I did say look at things from a steady state. So I wanted to determine all the V and I's. So VS, IS, V3 ohm, I3 ohm, VC1, IC1, VL and IL, V4 ohm and I4 ohm, VC2 and IC2, and V5 ohm and I5 ohm, right? Those are all the elements you needed to do. But I said to do it in steady state. Another way to say steady state is T equals to infinity. What happens to a capacitor at infinity? Open circuit. What happens to an inductor at steady state? Nothing changes with the resistor. What type of circuit do you have? Series circuit. Do you think you could solve for the current? Once you have that, does this voltage here look like anything that might help you? Does this voltage here look like anything that can help you? It's just going to be the voltage drops across this part, right? So you have this plus to minus voltage drop and this plus to minus voltage drop. Or you could have gone this voltage here minus that voltage should have been giving you the same thing. That's it for problem 2. Fair, not fair? There, yes, thumbs up on this one. 1, 2. Okay. Is it a reasonable question? Because this one the first 2 problems I was hoping that were going to be fairly short, quick, looking at the circuits, coming up with answers. Nothing tricky, nothing up my sleeve, just, going through what we've done many circuits, right? T of 0 minus, T of 0 plus, T of infinity. I basically said the first one was, what does T of 0 plus equal, right? And if you'll notice, the voltage and the currents were given to you to be very specific. Can the voltage drop across a capacitor change instantaneously? No. So the 8 volts stays, doesn't it? Can the current through an inductor change instantaneously? No, it cannot. Now, you could have said it would have been an impossible problem if I had swapped the current and the voltage, right? And said, here's 8 volts across the inductor, and here's 3 ohms in the capacitor. That would have been a much tougher problem. But by doing it without the fact that it has any changes, hopefully made it more straightforward. Any other comments or questions on problem 2? Okay, problem 3, cosine of 2t. We did this for homework, didn't we? Remember how I said Euler's identity, e to the j theta is equal to cosine of theta plus j sine theta? So e to the minus j theta is equal to cosine of minus theta plus j sine of minus theta, right? Yes? But we said that the cosine of minus theta, right? Cosine of minus theta equals the cosine of theta. And the sine of minus theta equals the sine of theta, but the negative, right? Because if we did our axis, this is plus, minus, sine, and plus, minus, cosine. So if you just draw your vectors there, you can see whether you have pluses and minuses. So essentially, e to the minus j theta equals cosine of theta minus j sine of theta, right? E to the j theta plus e to the minus j theta equals, so I've got a cosine here and a cosine here, that's 2 cosine theta, a minus j theta and a plus j theta plus 0j. So cosine of theta is equal to e to the j theta plus e to the minus j theta over 2. Couldn't you stuff that into your e to the j theta plus e to the minus j theta over 2, e to the minus st dt, and integrate it out? Some people try to do integration by parts. I don't see how you could do integration by parts, because if you integrate the sine and the cosine, you end up just you can't get rid of t. So the idea of doing integration by parts is to get rid of t terms, right? To get t down to dt essentially, so that you don't have to keep integrating it out of there because you get stuck. But over here, there's no t, right? Over here, this is just, this is omega t. And so I can combine these elements pretty easy into one single t term that integrates out. And that's why it's much easier to do Euler's identity to get this one. Fair, not fair? A little more challenging? Definitely less thumbs ups on this one.
Honestly, there wasn't a homework problem on that. I mean, I think you may have mentioned that we needed to know how to do it, but I don't think we actually did homework.
I'm pretty sure there was the cosine one you derived it at home. I think we did the sine in class and you did the cosine, or you did the cosine and we did the sine. It wasn't the notes, but I'm pretty sure we did a homework problem for that too. Did I miss?
Told us that we needed to know how to do it, but I think we voted probably against our own issues.
Is that the case? Did we not do that as a homework problem? We did or you did not?
We didn't vote for homework a lot, so we probably.
Oh, okay. You did not vote. All right, well, that was my mistake. I thought we had collected that one. So you can finish that if you want. Number 4, we did this one in class. So you want to take the Laplace transform of f of t equals t. So that's the integral of 0 to infinity t e to the minus st dt. There's no way of combining it, right? So you have to do integration by parts. If you let u equal t and du equal dt and dv equal e to the minus st dt, then v you'll calculate it out to be equal to e to the minus st over s. And then you plug that into your formula for integration by parts, which is u dv equals uv evaluated at your integration limits. In this case, it's 0 to infinity, minus v du integrated. And you should be able to come up with that one fairly quickly. Okay? Questions? Any questions on that one? All right. On number 5, I said here's f of s. I wanted to find what is f of t. So remember, we have to make the denominator look like something in the tables. Well, the first thing you can see here is s can be factored out of all those terms, right? So f of s is going to be 2 over s times s squared plus 8s plus 16. I have something now that may or may not be obvious to you, so you do the quadratic equation. Right? So my f of s becomes 2 over s times, you've got 2 roots at s equals minus 4, so that is the square, right? How do you do partial fraction expansion there? Most people forgot to do that last term, right? When you do partial fraction expansion, if you have something that is raised to a power in the denominator, you can't just forget about it. You have to bring it all the way down so that the order of the denominator is s to the 1, essentially, right? So if people got that one incorrect, it's because they forgot that s to the 4 last term. And you can always check your work if you have time, just by going through and multiplying it out, putting it back under a common denominator. Do you get your original terms? And if you had done it the way with just a and b, you would not have gotten the correct partial fraction expansion. So because you have an s plus 4 squared here and an s plus 4, you're going to have to do the derivative approach, right, that we showed you how to do in class to solve for the coefficients a, b, and c. Fair, not fair? I don't know how to make it grab the whole thing. There we go. Doable, not doable?
I think so. Let's do it.
Okay. Any other comments on number 5?
What is the derivative approach again?
So to solve for the derivative, if you want to solve for c, right? Whoops. You take 2 over s times s plus 4 squared, multiply by s plus 4 squared. Right? So I'm multiplying both sides by s plus 4 squared. right? Now I'm going to cancel out terms when I can. And I have 2 over s equals a times s plus 4 squared over s plus b plus c times s plus 4. I want to solve for c directly, and I don't know a and b. So if I take the derivative of 2 over s with respect to s, take the derivative of a s plus 4 squared over s with respect to s. What's the derivative of b with respect to s? 0, right? It's a derivative of constant. What's the derivative of d c times s plus 4? Just c, right? So I know when I take the derivative of this, it's going to be, it's the derivative of the numerator times the denominator minus the derivative. So we go 0 times s minus 2 times s squared, all 2 times 1, sorry, all over s squared. That's the derivative of this one. If I take the derivative of this, I know that I'm going to have a 2 times a s plus 4, right? If I evaluate this whole thing at s equals minus 4, doesn't that term make that go to 0? So all I'm left with is negative 2 over s squared equals c when I evaluate at s equals minus 4. So I take the derivative term so that I can get rid of this b. And since I'm still having an s plus 4 multiplying in the numerator there, it's still going to turn out to be multiplied by 0. So that's why I do the derivative, get rid of the b term. Because if I just multiply by s plus 4 and evaluate at s minus 4, that cancels out the term I'm trying to solve for, right? I don't want to get rid of the c term. I want to get rid of b. So by taking the derivative and then evaluating at s equals minus 4, then I'm in better shape. Okay? Number 6. So VC of t equals 5 times 1 minus e to the minus 4t. How long does it take to calculate, to reach 3.16 volts? Set it equal to 3.16. Solve for t. Questions on that? Fair, not fair? Okay. Number 7, we have an f of s equals 6 over s squared plus 2s plus 10. I don't know what the roots are, right? So I'm going to go ahead and factor them, or try to factor them by using quadratic equation. So negative b plus or minus the square root of b squared minus 4ac all over 2a is negative 2 plus or minus the square root of negative 36, right? Which is 6 times I, or 6 times j, all over 2, is equal to negative 1 plus or minus 3j. So f of s is equal to 6 over s minus the real root, or real part of the root, plus the imaginary term squared. Do you have any partial fraction expansion to do here? No, there's no two functions that are multiplying by each other. This one already looks like the table. You just need to go to the table and do whatever manipulations you need to make it look exactly like the table. And you got the answer. Okay? Questions on that? Some people try to say this is equal to a at an angle of theta. It's not right. How would you do partial fraction expansion? If you did that, you should have ended up with 6 again, right? But you couldn't do that anyway because if you evaluate it at this root, it cancels it out, right? But ultimately, it would just still be 6. So I don't know. A few people said they were trying to, to get that to work, but it doesn't get there from here essentially. You should have gotten that this, if you did it this way, would equal 6. If you don't believe me, right, this is s over 1 squared plus 3 squared, right? Evaluate at S equals minus 1 plus 3J. Plug that into here. This goes to, if I multiply both sides by what's under here, that cancels that out. That cancels that out. Let me do that again, just to be very clear. So there's no confusion. So 6 over S plus 1 squared plus 3 squared is equal to A at an angle of theta over S plus 1 squared plus 3 squared. Now I multiply to solve for the A coefficient. I multiply both sides by what's under this term. 6 times S plus 1 squared plus 3 squared equals A at an angle of theta multiplied by S plus 1 squared plus 3 squared over S plus 1 squared plus 3 squared. Evaluate at S equals minus 1 plus 3J. Don't those terms cancel out, and isn't A just equal to 6? Right? Remember what I said you should have ended up with 6? You don't have any partial fraction expansion because there isn't another term. There isn't another f of s term. There's a single f of s term, so you were done. You couldn't go any further. Questions on that? Fair, not fair? Should I wait a few more minutes to describe if you think this was a fair or not fair problem? One of the easier ones? Okay. Any other comments on that one? Number 8, 5 volts, 10 volts, and 2 Henry. What is VL of T and IL of T? What type of a circuit is this? First order circuit, second order circuit? First order circuit. So can't we use the Y of T equals A plus B e to the minus T over tau? So you needed to solve for VL of 0, VL of infinity, IL of 0, IL of infinity, right?
I think you only asked for I on this one.
Oh, okay. Even better. Let's get rid of that one. So if there is no charge on the inductor, what does the inductor look like? Looks like a current source. How many amps are flowing through the current source? 0, right? Because there's no initial condition. So this is the T equals 0 plus. Can you solve for IL of 0 at this point? And let's look at the T equals infinity. This is 5, 10. What does an inductor look like in steady state? Could you solve for IL there? And the last thing you need is tau. What is the time constant for a series RL circuit? A few of you actually did the full-blown derivations. Remember where we did the I of t equals A e to the minus alpha t plus k approach, which is fine. That's the brute force method, but that works. But this approach here, we presented it in class and it was perfectly fine to do in this one. Fair, not fair? Yes, sir.
What was the conclusion?
I'll let you work on that.
Okay, well, I don't know.
Any questions on number 8? Do we need to go over number 9? I'll give you a hint on number 9. Use a Thevenin equivalent, and the answer may be obvious. Number 10, we had to do VL and IL of T. So all I suggest on this one is we want to go ahead and do the T equals 0 plus. So this was the most amount of work. 0 minus. This was the most amount of work in my opinion. This is T equals 0 minus 10 volts. And just get rid of stuff that isn't relevant, right? What does an inductor look like in steady state? Can you solve for VL and IL here? You actually only need IL of 0 minus. You don't even need VL of 0 minus. Then we do T equals 0 plus. Now we're going to switch to the 5-volt supply. What does an inductor look like immediately after a transition has occurred? An ideal current source whose current matches whatever value you had. Can you solve for VL of 0 plus and IL of 0 plus? IL of 0 plus is the same value. You just needed to do a little bit more work to solve for VL of 0 plus. And then the T equals infinity. 5, 3, 4, and short. So VL of infinity should be pretty obvious, and IL of infinity is one additional calculation. And that was your test. What did you think? Was it as expected? A little harder, a little easier? Did you find that time was an issue? You ran out of time? Well, again, moving forward, the goal will be to do it during lab, which doesn't give you a huge amount of time, but it's, more than a 50% increase in time. What else?
How many problems with 3 and 4 because of bad integrals?
Bad integration? Pretty okay? Well, the reason why I did do the couple of derivation problems before we actually did Laplace is I just want to make sure you know what the tool is, because you know when the tool has its limits. And so doing just a little bit of calculus, and really because Euler's identity, we'll use it a lot, especially if you track towards the power trend. You use Euler's identity a ton because that's where we convert complex numbers back and forth. You use Euler's identity to do that. Makes it much easier. Anything else?
So from here on, how many more exams do we have?
One more and a final. If you took a look on Blackboard, you should have seen what your current grade is. Obviously, we don't have, all the labs, the 2 exams, but it gives you a better sense of where you are. And if your grade is not where you hope it would be, it gives you a chance to look at it, reflect, and then come talk to me about how you can improve the grade if you aren't seeing something. So it just gives you a chance to do that. I only do it after the second exam because the first exam, if you bombed it for whatever reason, I don't want to cause you undue anxiety. So usually after a couple exams, if you're struggling, then it's worth looking at more detail. I will make you an offer. Anybody interested in gambling? How about plus 20 points on your test? All you have to do is redo what you got wrong. That's why I didn't give you any of the answers. I showed you how to do it. Because I'm not giving you points. You're earning them, right? By going through and seeing if you understand how to do it, by redoing the problem and seeing if it makes sense. So turn in your test on Tuesday with the corrections. Make sure you turn the test in as well as the corrections in on Tuesday. Make sure it's neat and organized so I can find it. And again, I want it to be neat and organized to make it easy for me. But if it's neat and organized, that's also going to help you when you study, right? So going through and being clear and laying things out properly, you'll find that it's going to make it much easier for you to review it and understand it. So if you just do chicken scratches and you just throw things on there, the exercise is to hopefully learn the material a little bit better. So, deal or no deal? You have a comment? I hope so, yes. Actually, no, it will not. Because not everybody has taken the exam. So, well, you know what? I will make it available, and then for those who haven't taken the exam, we'll have to figure something else out. Okay? So, yes, it will be up. Unless you don't think it's helpful, then I won't put it up. What's the laugh for? Is it not helpful, or is it helpful? I don't know. I'm asking.
Very helpful.
Okay.
Do you have an average? I know you said not average.
No, because like I said, not everybody has taken the exam. So, I mean, I can, I think it was a 60-something, but I don't know exactly. What's that? Okay. So you're accepting the offer? Actually, you know what? You can do it individually. You're under no obligation to turn it in. If you're satisfied with your grade and you don't want to spend the time doing it, that's totally up to you. It does not count against you. It's not a negative. I'm not going to record this and say this person did not turn in the 20-point opportunity bonus, whatever. So you're under zero obligation to turn it in for what it's worth. So it won't count against you. But if you want to earn additional points, then that's totally your call. Okay? Fair deal? All right. All right, let's stop this one at 32 minutes, and then we'll pick up chapter